slightly regret that I requested a fancy introduction, but I mean, okay. So thank you very much for giving me an opportunity. I mean, thank you very much for giving me an opportunity to give a kind of several talks here. And so what I prepared is actually more like kind of elementary topics in the study of reverse math. So I'm afraid many of you already know major part of that, perhaps, but I hope at least, I mean, you may find some tips. Okay, so I'm trying to just start again from the introducing the subsystems of Z2. I mean, just for a very casual introduction. And then so as you have seen already, of course, the systems are usually characterized by induction and comprehension, right? And then, well, actually, the major systems of Z2 is can be usually characterized by some comprehension, like P comprehension means the statement something like, so there is I always skip the kind of a universal closure. But the real statement is always taking universal closure of this kind, but the like for any n, Pn, if and only if x, right? And and then something like let's just say gamma comprehension, and then it's from gamma, and then gamma separation. It's something like if for any n, Pn 1 happens at the same time. Then there is such that the what's that? So the always get confused. For any n, Pn implies n in x, and Pn implies not a member of x. So that's the separation. And also, of course, the induction. I don't like gamma induction, but you know what they are. Then okay, so the major big five is easily described by just this kind of comprehension, right? So number one, RCA 0 is just the let's say PA minus plus sigma 01 induction plus I didn't introduce even delta 01 comprehension, but maybe you can like pi 01 separation actually if you write in a kind of a simpler way, and then the second system is just this plus sigma 01 separation. And the third system is just sigma 01 comprehension, or like pi 02 separation, for example. It's all the same. And the fourth one, ATR 0, is just this plus sigma 11 separation. And then one comprehension, system of pi comprehension is just this together with pi 11 or sigma 11 CA. Pi 02 separation, or yes, any kind is fine indeed, but yes. So we often use big 5 system, and then actually big 5 is, in a sense, so really the system of comprehension. I mean, if you agree that the separation is also a comprehension axiom, while I mean many other, of course, nice, interesting principles. I mean, independent from these are known, but usually they are not like exactly the form of like comprehension. But still, I mean, there are many other things. But of course, I mean, we may probably, if we think about the linear math from kind of a broader view, probably we can first think about the hierarchy of comprehension from below, and then so that's why Big Five is so important in a sense, I think. And so with this, okay, I mean, so when I was in postdoc in Penn State, Steve Simpson often gave a kind of a tutorial taught in many places, and then he often says that important systems are mostly linearly ordered. I mean, you might agree or maybe not, but often Simpson says that, and so I just try to draw the map of that. So I'll say 0, probably the bottom of, well, let's start with I'll say 0 star because Ludwig introduced already the I'll say 0 star. This means the induction weakened to a delta 0 1 level. That's the main difference. Plus the yes. And then I'll say 0. And I will later introduce the system called WWKL0, but this is not Big Five, and this is not easily characterized by more like a comprehension style axiom, but it's between WKL0 and WKL0 and RCA0, and then SCA0, and then like the system of like delta 1 1 comprehension is here, sigma 1 1 choice is a bit above it, and then ATR0, empire on comprehension, not enough space, but Z2, and of course more and more, the level of set theory. And then if you like compare with the, so RT22 is, for example, somewhere around here, and there's a huge reverse mass Z here. Maybe more about this area, probably. Like Heinemann theorem, or can you argue many other things above it, actually. And then if we compare the, strength of the first order system, so this is all this, of course, the subsystems of second order arithmetic, but if we compare with the first order system, then like I sigma 01 is here, and well, this is more like a level of EFA, or I B sigma 01 plus exponential is the level of RCA 0, and so the level of I sigma 1 is just RCA 0 and WK 0 both with the level of I sigma 1, and then this is the level of PA, and actually PA is on here is all PA, and then get stronger. But so like from here, probably first order version is more like a set theory. ATR 0. So the connection between them is kind of strange. You may add like, so PA can be considered as an ATR 0 set minus infinity. So in a sense, this is still connected, and then you may have to the level of maybe GSC and more. That's the big picture for me. When I think about the strengths of systems, and well, by the way, so now I'm often asked about the strengths of induction. In many contexts, and then so sometimes you may easily, because this is summer school, so I'll try to just make some remarks. And then so if you're consider the strength of induction. Okay, so from the level of ACA 0, maybe the level of sigma 1 axiom of choice, then, okay, so just compare the strength with induction. I mean, induction of natural number is kind of reasonable. But above this level, I mean, so actually, I see many students misunderstand that the, like pi 1 CA 0 is a level of pi 1 induction. But this is not the case, actually. I mean, so above the level of ACA 0, the second order induction doesn't provide doesn't provide a strong axiom, actually. So like, for example, ACA 0 plus, I mean, like, even the full induction, pi 1 full induction, the consistency of this is just below so-called ACA 0 plus, for example. So ACA 0 plus, I mean, I haven't introduced the system, but if you know what that is, I mean, it's essentially saying that there is an omega jump of any set. That already implies the ACA 0 consistency, or I mean, existence of a model of ACA 0 plus pi 1 ACA 0 plus full induction. So please, I mean, I draw this kind of picture, but the level of induction 1 goes up from the level of PA. So that's one kind of a small tip that I mean. And okay, by the way, and on the other hand, induction sigma ij induction can be often considered as a finite comprehension, so-called bounded comprehension. So like sigma ij bounded comprehension, meaning that the so for any sigma ij formula P, you may find some x. So for any n, you may find x subset of to n. I mean, so this is, of course, n can be non-standard, so this is informal way of writing, but you can still understand the meaning. And then such that, I mean, for any, well, I already used n. So for any m less than n, P of m, I mean, yes, P of m is not only if m is a member of X. So this is always equivalent to induction. So induction can be also considered as a kind of a comprehension. And by the way, so why I wanted to introduce this, because just because the equivalence of, so the proof of this is, I mean, mentioned everywhere. I mean, all basic logic. I mean, arithmetic textbooks, but very often the proof is kind of long. But it's actually, there is a very short proof. So I just want to introduce that. I mean, so the induction actually always implies bounded comprehension, and then so we can actually show it easily. So let's say, so like let's just consider the case. I mean, consider the case of sigma 1 induction. I mean, all other levels, sigma 0n or sigma 1n, all other levels are the same, but the sigma 1 bounded comprehension. How can we prove it? It's actually just very easy. So okay, let's say theta m is something of the form there is z, such that theta 0 and z. So this sigma 1. So this is theta 0 is arithmetical. And then, okay, we may consider the formula C of k, saying that something like a, so there is y, and there is, well, so this is actually just a number quantifier. So finite subset of M such that, well, for any M in X, theta M and M slice of the M segment of Y is the witness for this theta 0. And the finality of X is bigger than K. Consider this type of statement. And then we have, okay, what do we know? Then we can easily check that C0 and C, well, not Cn plus 1 holds easily, because I mean, X is a subset of 0 to n, so not Cn plus 1 holds. So by induction, because this is C0 not Cn plus 1, and this is just sigma 1, 1 statement, I mean, you can carefully check that this is 1. So meaning that, okay, there's some L more than n plus 1, that CL holds and not CL plus 1. But CL holds, so we'll pick the witness X for this CL. That's the desired set. You can easily check. So I mean, if you haven't experienced, like, struggled with the proof of boundary comprehension, which often happens in our logic group in Tohoku, but then yeah, or some students are in trouble with the boundary comprehension. It's probably one of the shortest proofs. So I just wanted to introduce it. Okay, and then I didn't explain several things yet, but I mean, so for my talk, I will mainly work first within the level of RCA0, WTA0, and then CA0. And then the latter half of my talk will be a bit more about, like, the reverse math for pattern comprehension a bit. But for that plan, I will try to just, I mean, review what kind of things are available within first three systems at first. So for example, within RCA0, what we can do is that, I mean, so the RCA0, of course, is a system for, like, more like a computable math, right? And so what is important is, of course, I mean, well, first of all, we can always code in for, like, as finite sequences. Those are available, and of course we can talk about function as a, I mean, by considering the graph, and then so we can also consider a sequence of, like, sets or functions by, well, I already used the notation here, but like this. I mean, meaning that if Y is a sequence of sets, means that, I mean, you may consider Y is a sequence of, like, something like this, and where Ym is just a set, I mean, X such that, well, the pair Xm is a member of Y. I mean, I'm quite sloppy. I mean, I might use a different definition sometimes, but I mean, you can easily guess the meaning. I mean. And then what's more important is, well, within RCA0, we can always use a primitive recursion. Primitive recursion is available within RCA0, and actually the point is that a function defined by primitive recursion as an implicit definition of a function, then it's total. That's the point, actually. And it is total. So that's the point of the primitive recursion within RC0. And actually, so this is indeed equivalent to sigma 1 induction already. And so, I mean, when we use kind of a primitive recursion together with some like zero jump, for example, then we need stronger induction. So yeah, so we should pay attention to that kind of situation. So that's, well, I mean, very brief sketch of what we can often use within formalizing something within RC0. And then, okay, then for the level of WK0, of course, I mean, I just introduced the system WK0 by sigma 01 separation, but of course, I mean, like the Kenny's lemma, I mean saying that any infinite tree, or if a tree is infinite, then he has a path. And like sigma 01 separation. And I may use in my talk almost without mentioning it, but the kind of a strongest form of WK0 is usually known as a strong pi 01 dependent choice. That's what. So what's that means the statement of the form like Pn xy is a pi 01 formula, then the statement is that, well, okay, there's always a sequence of sets Z. This is a sequence of sets. Such as for any n, well, okay, if there's something exists and the phi of n Zn y, then the Zn plus 1 is the witness for this one. So this is also equivalent to WKL. I mean, actually, well, we can consider this as the kind of a possible strongest form of the WKL. And so, I mean, well, instead of using WKL0, I mean, we can always use WKL with this form. And then I'm a little afraid that I used the board too much, but I have to erase at some point. Okay? And then, of course, so that was the characterization of the second level, I mean WK0. And then, of course, for AC0, the famous characterization is over LC0. The following are equivalent, and so I introduced this SA0 as a sigma 01 comprehension, but actually that's also equivalent to all arithmetical comprehension by easy induction. It's well known, and then I will use actually the full version of Kenny's lemma. I'm saying that for any, if a tree T, now, I mean, on their space, I would say, I mean, well, for sequence of natural numbers, it's finitely branching, and infinite, then he has a path. Right? I mean, that's Kenny's lemma. And also, I mean, so this is in a sense, so sigma-1 comprehension or Kenny's lemma is in a sense kind of a stronger formalization of the ESI0, while if you want to say something implies ESI0, then of course, I mean, many of you already well known, but the, I mean, following statement is also equivalent to ESI0, saying if a function from natural number to natural number, well, we may assume it's 1 to 1. So if this is a function, then its image exists. And it exists x such that x is the range of f, right? So this is probably the weakest form of zero. And when you want to show something, show ESI0 from something, then we often use this. Okay, and also I've tried to, well, introduce the system double KL. I mean, so okay, so so double KL0 is a weakening of double KL0, and actually I may probably use the following fact later or not. I'm not so sure whether I can mention it officially or not. But anyway, so over famous characterization is that with Kenny's lemma, this is the, I mean, usually the axiom, but well, 1.5 level between WK0 and RC0, and saying that so given a 3T on Cantor space, and if the length n members of T, the number of those divided by 2 to the n is, well, I mean, I want to write inf for limit or something. Inf of this is positive, then he has a path. And this is positive, of course, means that the 3T is infinite. So it's a special case of WKL0. And this is known to be equivalent to so-called Martin-West randomness. I mean, so for any x, there is y, Martin-West random relative to x. That's known to be equivalent to with Kenny's lemma over RC0. I mean, if you know something about Martin-West random Leo, then it's a if you don't, no worry. I mean, we don't need to use it essentially. Okay, so that's a more like very vague, I mean, overview of the subsystems of second order arithmetic. Okay, now I'll try to start some analysis. Okay. Yeah, I mean,
I think it's easier to read with them.
Okay, thank you. When I give a course in my institute, I usually write a lot. I mean, in like 90 minutes course, usually I override like 5 times or something. Sorry. Sorry about it. Thank you. Okay, so now, I mean, let's start. I mean, reverse math for analysis, but like, want to do reverse math for analysis. And I kind of know that this topic, well, was quite popular when the reverse math program started, like in 1970s, 80s probably, 1990s or so. And then it gets less and less popular topic, unfortunately, I feel. And probably because of the kind of a heavy coding. That's my understanding. I mean, many of you, I mean, don't like codes for like continuous functions, for example. So I've tried to, I mean, give a kind of a, well, I mean, equivalent definition, but a bit better way to understand what's going on in the basic definitions of like continuous function and the one there. So that's the aim of today's talk, I would say. So okay, but anyway, when we start reverse math for analysis, well, okay, first we have to define needed numbers and structures. So n is of course just the all numbers, or the domain of first order quantifier, essentially, that's n. And I don't want to give a definition, but the integers, rational numbers can be easily coded by natural number. You probably know well about it, I don't mention. And then real line. So it's usually defined by a strong quasi-sequence of rationals, I mean, of a member of Q. I mean, something like R, or what, yeah, R is can be considered Ri. So this is a function from natural number to rational, such that for any I and j, I mean Ri minus Rj, you can easily. So these are both rational, so it's already difference is already defined, and then this is smaller than 2 to the, I mean, I guess, yeah, maybe let's like I plus j, and here minus I. Probably it's the equation. So so this is a member. I mean, so yeah, member of real number is actually a set, right? I mean, strong quasi-sequence. And then, so for this important remark is, of course, I mean, we are working as a analysis, but from the viewpoint of logic, so always the complexity of the statement is very important. So if R and S are real numbers, then of course R is smaller than S. I mean, I didn't give a definition for this, but probably you know. And then this is pi01 can be described by pi01 formula, and split n is sigma 01. That's probably the most important part, the definition. And then now, okay. So now I've tried to point to a real math topic now. So we'll first do this like complete separable metric space, right? I mean, metric space, I mean Polish space. And then, well, I'll first introduce Polish space, and then we try to work mainly on really. But I mean, so Polish space is coded by, I mean, complete separable metric space is a pair, I mean, A and B, let's say. So A is just a set, and D is a distance function, A times A to, I mean, non-negative real numbers. I mean, usually, I mean, very often, just positive, or I mean, non-negative rational is enough. But I mean, if you want to encode like a Euclidean space, then of course the Euclidean metric is often not rational. so just for that purpose, I use real numbers. But actually, that's not essential. So if you want to reduce the complexity, we can always replace this with a rational number, and without changing the topology. That's the essential part, right? I mean, you can do that. And then, of course, satisfy the trigonometric, I mean, inequality and so on for distance function. I don't want to mention. And then, what's that? So the point of the completion of this A. So this is, of course, the countable dense set for the separability. But the point of A is what? So point is what? So it's a again strong cauchy sequence, right? I mean, this is a member of A, and then this is a sequence from M to A, such that for any I and J, distance between xi and xi plus j is always more than 2 to the minus I. That's the requirement. And then, okay, now, so given 2 points, and the distance between them is of course defined by a well, okay, so before that, yes, the distance between them is just the limit of distance of xi and yi. Right, and then, I mean, this always converges because of this condition. You can easily check it. And, well, actually, what more important is that this exists as a positive real all the time. I mean, so convergence is provable within RCA0 indeed. And, well, by easy checking. And of course, we will define 2 points are equal if the distance between them is 0. And so again, the point is this is either one statement. Right? And sorry, I wanted to add another thing. So this set A can be also considered a subset of the complete separable metric space by, so the point in A will be embedded to A. So A can be considered as a subset of A hat. And of course, I mean, as you know well, probably, so, I mean, for the case that A hat is real line, then of course this A can be considered as usually rational numbers, or maybe binary rational numbers, or something like that. I mean, depending on what you want to do. I mean, but I mean, there are many equivalent reformulation of, I mean, R, for example. So the, yes. Sorry. Right.
Now you get tested.
Yeah, okay. Okay. Now I got it. Yeah. Oh. Yes. Thank you. Okay. So, and then of course, important thing is of course a topology on the Polish space. So we'll try to use B as a basis for an A hat. Is a we may consider it as a something like this. So the A and R such that, well, A is a member of capital, small a is a member of capital A, and R is a member of positive rational number. And forms a open base for A hat. I mean, so we will always identify the pair AR with the ball centered by A and the radius R, meaning that the something like a member of A hat such that, well, distance between A and X is smaller than R. Again, this is sigma 1. And okay, so now, I mean, I'd like to just introduce the usual order on the base. So we mean, so AR is smaller than DS if distance between A and B plus R is smaller than S. I mean, the ball DS covers the ball AR. Right? So with this situation, we will use right in this way. And then one can easily see that member of X, I mean member of space, can be identified with this thing, Fx. So this is what? So AR, the member of base, such that, well, X is a member of ball. So correcting all those things, then, so that's actually a maximal filter D, right? So a point of a complete separable metric space can be always identified with a maximal filter on the yes, on B. And I mean, maximal filter means, so maximal, what maximal means here, actually, I mean, of course, maximal means maximal. But I mean, maximal, if you write in a kind of a natural way, it's I11, I think. But of course, in this situation, we can actually reduce the complexity. So this means that for any m natural number, well, there is a member AR in Fx such that the R is smaller than 2 to the minus m. This is good enough. Say that it's maximal. And I mean, you can easily check that. And also, I would mention that this is indeed like sigma 01 definable ideal, sigma 01 definable set. So this set may not exist as an object. I mean, as a set, but we can still consider this kind of thing. So just consider the sigma 01 definable set, or I mean CE set. And but if we identify a point with a CE maximal filter, let's say, well, the view is kind of clear, I think. Of course, an easy proposition is that so if F is a CE maximal filter, officially, to define a CE set, well, we can always consider like E. So officially, we can always consider F as a subset of n times D, right? And then AR is in F means, well, this is just I mean notation, but there is an NAR. I mean, so it's kind of a sloppy notation. I mean, I use the same letter, but I mean, one can always write C set in this way. I mean, always. I mean, C or sigma 01 boldface probably. I mean, that's better. Probably, but so yeah, okay. So given a CE maximal filter, then of course there exists unique edge in A hat such that the edge is just the intersection of all these things. You can easily prove it. And of course, well, I've already mentioned, but here, but of course, the other direction is also hold. So if X is a member of A hat, then F sub X is the maximal filter. Right? I mean, you can check it easily. So that's the characterization of points of complete separable metric space, I think. I can't reach the definition of. Okay. here. So the next thing is, of course, open sets. So open sets is, again, open set. I always, in a sloppy way, I will always use the same letter. But coded by C set of base, right? C set, C subset of B. And if you say it's a code for open set, then, well, X is a member of U, even only, if less than AR in U, such that the distance between X and A is more than R, meaning that the U is a union of these balls where AR is in U as an C set. Sorry for a very sloppy notation, but yes. And then, actually, not only open sets, but actually, sigma 0 M sets can be also defined the same way. So for standard natural number n, not internal number. For standard natural number n, we can also define, sigma 0 M sets, right? What I wanted to write A hat is the sigma 0 M set. It's okay. So now it should be defined by a n times B. And now the X is a member of S, if and only if you can consider like there exists M1 or any M2. Well, actually, it depends on the case whether n is even or odd. Definition might be different, but for example, if n is odd, then such that, well, these M1 to Mn and AR is in S, and what? And X is a member of. This N? Okay, so just to make this as a sigma 01 set. Well, indeed. Sorry? In a sloppy way, U is just a sigma 01 definable subset of B. So, yeah. Officially, we should write in this way. And okay, so in case n is even, right? No, n is odd, then definition is like this, and n is even, then of course x in S should be more like this M1 to the last one is for all. So for any A and for any R in S, I mean, for so if this is a member of S, then so X is not a member of this one. So then you may define like sigma 0 M plus. I mean, yes. And if you want to define pi 0 M in a way. Okay. Well, indeed, we can of course define in general like Borel sets using Borel codes, but I mean for that, well, RC0 is not so smooth. I mean, we can still define, but I mean, it's very hard to write this already. I mean, if n is non-standard. So now, I mean, to consider just, I mean, internal but finite level, okay, it's natural to assume ACA0 prime. And if you go up to the higher level, then usually over ATR0. Well, over ACA0, still we can define the notion, but the meaning is a bit more sensitive. So yes. So here, for today's purpose, just I mean, standard finite level is enough. Okay, I think I should stop here. Sorry, I can't reach to the more like kind of interesting part. But I mean, tomorrow I'll try to start a definition of a continuous function based on this, and then we will try to generalize this. I mean, continuous function to the level like sigma n measurable function, and then we can describe more things, and in a kind of a smoother way. And then based on that setting, I've tried to do some basic analysis. That's the purpose. That's the aim of this talk. Okay, thank you. Okay.
Thank you again.
Thank you.